Yeah. So, chalo, start karte session. Let's start the session, guys. So we are meeting after I think 1.5 months. So now let's start again. So today's topic is it's kind of a different topic. It's an augmented data structure. So so as you can see the overview, we would be covering monotonic structures today, along with nested structures, and it comes along with the practice problems. So, like as you know, your internships are coming in. I think most of you are from the second year, so your internships are coming in the next 3 months, 3-4 months maybe. So it's good to have a practice. The questions would be on the line of the online assessments that you'd probably expect. So let's start the session. So Amit,
So yeah, guys. So okay, so I want a quick review. Like, how many of you actually know about stacks and queues? Okay. So like, uh, is there someone who doesn't know like at least what the functions are? And how many of you know about STL stacks and queues? Like how it is implemented in just the function, the syntax and other stuff, right? Yeah. Okay, I think that should be fine. So we're going to start with the warm-up question, and the question name is next greater element. So I want to ask how many of you have heard about this problem, at least. Next greater element. It's literally the first statement or the first problem that you encounter while solving problems on stacks. Okay, maybe like you might not be familiar with the exact wording, but let me just read out the problem statement. So you are given an array, and we need to produce another array where each element of the array B, like BI, should be next greater element of AI. So if I say 6, for 6, the next greater is 8, right? The next greater is 8. And similarly, if you think about 8, you can no longer find any element in the right side which would be greater than 8. So we output -1. For 0, the next greater is just 1. For 1, the next greater is 3. For 3, there is no element present, so we output -1. So I hope you have like read the problem statement. Yeah. So I want you guys to again think, have you solved this problem before? It's like second year, so like at least heard about this problem. No one? Okay. Okay, that is fine because I'll be just starting from complete design perspective. So there are like a few kind of people who have actually seen this problem. Type 1, who have just read the solution, like they tried on their own and they didn't find the solution, and they just kind of remembered the solution. The other type of people are who have actually tried this problem and find out or designed uh, a data structure to implement this. And third type of people who have understood the pattern. So we'll be focusing on the third type. So we'll be starting with the design, and similarly, as we proceed ahead, we'll try like if everyone just understands the pattern behind this. So I'll be starting with a brute force. Can somebody give me a brute force approach for this? Yeah, two for loops. Yeah, yeah, yeah. So if this question comes in OA, which I think most likely it won't come, but if it comes, then 50% of cases would pass on O of n square. So at least like giving a brute force solution could help like rather than not giving a solution at all. So I would like to just uh, take it from you guys, like what are the observations that you can make out from this and suggest a better solution. Okay, so I want to confirm at least all of you have understood this problem statement correctly, right? Because like most of you haven't heard about this problem. All right. So I want you guys to focus on these key observations. So, okay, I'm going to ask you two questions. Suppose I give you a segment of the array. Let's say I give you a subarray lying between L and R indices. And uh, for all elements, this condition is satisfied. Like AI should be greater than equal to AJ, where J is greater than I. So it is kind of a decreasing array. You think about that? It's a decreasing subarray. So suppose I give you only this array and I want you to find the next greater element for each element. So what should be that? So just think about it. Okay, so let me just give you some example. So let's say you have an array like this, and yeah, equal to is also there. So maybe we can take 5, 5, and 2. So if you want to generate a next greater element array from this, so what is it? Yeah? Yeah, correct. So for all these elements, you won't find any number which is greater than this element. Suppose we pick this element, there is no element which is greater than equal to 8. Sorry, greater than 8. So that's why, right? So think about this test case. Why did we consider this array? The reason is because it gives us the answer, right? So if we assume that our goal is to just create this array out of the complete array, then we already have our answer, right? All minus ones. Okay, so let's say we assume one is like holding true, and suppose one becomes false or one is violated at any point. So suppose a number like 7 comes here. If a number like 7 comes here, then all we need to do is fix this number somehow to regenerate this array, right? So one thing is we were given this array for which we know the answer, and if we face a violation, this is a violation, and if we are able to adjust our answers or like take care of this violation so that our array is again decreasing, then we will be able to solve this problem. So what I am trying to say is 1 and 2 are sufficient to solve this problem. So if you are, it's like you are trying to maintain a data structure, right? So let me give you a classic example. So let's say you have a tree, right? I think how many of you know about binary trees? Yeah, balanced binary trees, AVL trees, red black trees, all it. Yeah. Okay, that's fine. Like so, let's say this is a VST. What do you do in AVL is you perform rotations to balance the tree, right? So it's not like you are like directly changing the data structure at all. It's like at the point of insertion, you are performing some rotation so that it becomes balanced. So essentially what you are doing is you are balancing that binary tree. So similarly, we are trying to maintain this array in such a way that it is monotonically decreasing. And for each element, we can just output -1. And if we face any kind of violation here, then we should be able to fix that, right? So let's have a visual representation, like that would be much better. So again the same approach, like you think of this graph as denoting the elements. So let's say you can see all the elements are decreasing, like non-increasing. And suppose you face some violation at any point. So if you face some violation at any point, so let me just draw this. So roughly this figure is there. So what my approach would be, so I couldn't find any greater element for these elements, right? For all these elements, I couldn't figure out. But if I think about this line, so every element less than this line would have this as the next greater element. So all of you agree to that? The reason is because you weren't able to find for any of these array element points, and you find out a violation, and all the elements were basically less than that. So this should be the next greater for this, and this, right? Right? So we figured out the next greater for these elements, and now suppose we are able to just finalize the next greater for these elements, right? We have kind of finalized that this is the next greater for all these elements, and then we can add this to this array only. So it would change to this array, right? So again, we have a decreasing data structure. So what you have essentially done is you have fixed the violation, you have predicted the output, and now you have maintained the data structure to its original state, right? So, and now I am going to ask you one question. So this is the whole approach behind this question. So I want you guys to, how would you perform this implementation? Like I want this data structure to be converted to this. Are there some ways? So, but my question is, suppose you are given something like this, and this point is given to you, this whole array is given to you, and I want this data structure out of this, and this plus the next greater element array for these points. So any approaches? Okay, maybe if I represent that as a number, then it would be fine. You have 9, 8, 7, 7. Maybe let's have it a little more, or 5, 4. And then suppose you get this array. Then I want this array to be converted to this 9877, 98775, 65. Yeah, 65. 5 and 4 should be eliminated because the next greater element is 6. So I think this is the data structure that we want. So are there any implementation ideas? Okay, so in one of the sessions, you might have noticed there is a trick called binary search, right? So if you have a sorted array, then you can perform a binary search to find like where this element could possibly be inserted. It's like a find function. So you find the position where this element could be added, right? So if you are able to find that position, so what I'll do is, suppose this is the position, right? I find this position. So it is discrete point, so it would be like kind of this, or it depends on your implementation. But if you find such position, then I can just eliminate all these elements and assign the NGE for these elements as this point, right? I didn't do anything. I just found out the correct position for this element and eliminated all the elements, assigned them the NGE as this element, and yeah, my data structure is like this now. So this idea is not very used. Like the time complexity for this is n log n. We will discuss about the time complexity, why it is like this. So this implementation could be done using maybe a set or map. So I hope you know about sets and maps, right? And the time complexity is involved. So let me just revise the concepts here. So for sets or maps, there are few operations. Like you can perform find in set or map in of log n. Similarly, you can insert in log n, you can delete in log n. So it's a very flexible data structure. Like if you don't want to care about the implementation and just are not specializing about something or a special property, then you could use a set or map to implement this idea. So, okay, this solution works, but it will pass 90% of the test cases. So it's a very optimized approach, but uh, it takes n log n time. So I want some of an algorithm. And O of an algorithm is simpler than this algorithm. So could you just spot it? So I again repeat, I want this data structure to be converted to this data structure. So is there a way? Yeah? Yeah, stack, yeah. Yeah, yeah. Yeah. Yeah, so all we need to do is keep on, like we will just store them in stack, and we will just keep on removing until the element here becomes greater than that, right? So we are basically saving this thing. We are not finding that the correct position, right? We already know that when my this element, so I'll find this element as greater than this, then I'm going to stop. So you can see that this is like this way, then you will remove this, then you will remove this, then you will remove this, and yeah, that's where you stop. So you can see that it is uh, last in first out kind of thing, so it is a stack, right? So okay, so enough of the theory, let's just look at code, and hopefully you will find some better understanding from here. So if you just look at this, so the first thing that you are going to do is, so let me just clear the board. So the first thing is very simple, like we initialize a stack here. And the next thing is like, I want to also tell you guys, like some people get confused regarding the implementation, and I want all your doubts to be cleared. So we have a stack here that is like a must, that we just discussed that for the most optimized approach, we need a stack. And now the next thing you are going to write is a for loop, right? You have like the normal for loop. We'll just iterate over this array, whatever array is given to you. And the next thing is that I mentioned in the first point itself that we want to maintain that data structure. So our first thing would be adding to that data structure. So we'll add our element, let's say of I, right? Now just think about this. What we are doing above is like, here we are trying to fix the violation, right? That's how simple it is. Fixing the violation is just like going back and converting that data structure to that, right? So that's all about it. So that's just a while loop, and we are just ensuring that. So if we have two elements, like suppose I want to insert in this position, like we have this, then I'm just ensuring that whatever is at the top of the stack, say this is the top of the stack. If it is less than array of I, then remove it. If I remove it, and yeah, this is already greater, so we don't have to do anything. At the end, we'll push that element in the stack, right? Now this is, you might be thinking about why I'm pushing I here, because uh, there could be duplicate elements, so it is better to just push the index, right? So we won't have any kind of corner cases at all. At the end, we know that okay, we have just maintained our data structure, and we know that our final data structure is going to look like this, and the answer for all of them is -1. that that's like a very simple thing, right? So to be clear, like this is a very warm up type of question, so which is never asked in an interview or in a coding round. So we'll move ahead to, so all of these questions that I'm discussing are standard. So we'll be also discussing some the current question that are asked in OA. So, so this is the templated code. So you could just look at it. That's how the things work. And it's just a mono stack. So what I just told you is this kind of data structure, right? Suppose I have this kind of data structure here, and I want to maintain this kind of data structure. Then you could use the same templated code and just change the condition. We'll look at that in the next example. So yeah, so that's an important thing. About the time complexity, many people just confuse it or never completely understand it. For CSE guys, how many are from CSE? All right, so almost all. So I think Ajin sir took your classes and might have taught you about time complexities, right? So I think you might have already figured out what is the time complexity. So can somebody say why the time complexity is O of n, not anything else? Because we have a while loop inside, right? And now our general intuition says we have a for loop and then a while loop. The time complexity is can't be, or like it doesn't seem intuitive to be often. So any reasoning for that? Yeah. Yeah, that's correct. So the idea is like, okay, so let's say this is fixed. This is going to run for n times, correct? This is going to run for definitely for n times. We cannot change anything. It is very fixed. But this thing is this is a variable. So let's say in the first iteration it runs for k1 times. In the next it runs for k2 times. Third iteration runs for k3 times and till kn. So overall, if you consider a weighted thing, so weighted sum. So if you know about weighted sum, so all you so this all the weights for these iterations is constant. So in the first iteration, it should be k1 plus k2 plus k3 times this till kn. So this is going to give you O of n, plus there would be an additional O of n from here, because there should be a iteration time also. This is the iteration time, which is 1 units. This is the iteration time, which is k1. So it is k1 plus 1, k2 plus 1. So if you just sum it up, we'll get off to 2 times n, which is often, right? So I hope this doubt is cleared. If you have any more doubts, just clear it, because next problems are going to be, yeah, a bit involved. Is that fine? So the reason why I'm telling you through this way, like I don't think so anybody will tell you in that way, is because you won't find this design thing out there. Whatever we designed, we just spotted the observations. This is not something that you will find. You will just basically be memorizing at the end, and that approach works for all the cases. But I just wanted to teach you about the designing of data structures. Yeah. And so we have this problem too. So another standard problem, but it's like I don't know why it is lead code hard or DFG hard. But the thing is, like, the idea is just a two-line idea. If you know about monotonic stacks, like I just discussed earlier. So just read the problem statement. We need to find the maximum rectangular area possible in the given histogram, where the largest rectangle can be made of a number of contiguous bars. So I think just by looking at figure, you'll have realized like uh, what the problem statement is and what we need to find. So is the problem statement clear for everyone? So I want some observations. So every question has observations, and answering these observations is sufficient to solve the problem. So there are a few observations. If you can tell me, I'll just explain. Any kind of observation is fine. Okay, I'm going to give you a hint here. Yeah, could you be a bit louder? Yeah. That's not true. Like it could be there, but if you give some example, I'm going to give you a counter example. So if you generate an input, I'm always going to give you an output. So that won't be passing on every test case. Yeah. So, okay. So one thing you are stating is that you are going to focus on the one which has a minimum bar length. Yeah. Just clear this up. So yeah, your idea is you're going to focus on. Okay. So you are trying to like adjust something like this. If I'm able to find something like this, then uh, like what's your approach? I didn't know. So yeah, this is the one which has the smaller height. So you are trying to just start at any index, and I'm just gonna say this is the height, and for the next one, I'm just considering this height, and you will proceed ahead, right? Okay, so yeah, yeah. So that's brute force. That's O of n square. Am I correct? The approach you are saying is has a time complexity of O of n square because for every element you will be performing this operation, right? Yeah, for O of n square. Okay, that's fine. You will pass around 50% of the cases. So if you want to optimize it, okay. So I'm going to give you a hint here. Okay, I want you to focus on 4 here. So what is the okay? If you look at the diagram, what you can say, like I have 4 here, and this is like minimum in its surroundings, right? If you just look at it, it's the minimum, right? It's the minimum in its surroundings, so like you are just considering it. But if you find some other element which is a smaller element, say 3, then obviously you cannot extend it, or you may or may not, uh, uh, but this is not like not optimal for your answers, right? You're able to see that. Let me just go to the observations. So assume that my current element is the bottleneck. So we'll have a bottleneck in every rectangle, right? The one with the minimum height. So assume that you have somehow magically obtained that bottleneck, right? that that of course we are not going to find magically, but just iterate and just assume that this is the bottleneck. Then what can we say? I give you the bottleneck for this rectangle. Bottleneck by the definition, it means that it is the smallest number which would be present in that histogram that you are looking, right? So if you find some lesser number, that definitely that's going to violate that principle that this is the bottleneck, right? So if we just have a bottleneck here, then we are definitely ensured that all our elements from right and from left are going to be greater than equal to 4, right? Is that fine? Is that fine, like this thing? So this also means that if I am able to find the next smallest element, so it is like the next smallest element, then I already have my answer, right? If I find the next smaller element from this end, then I know I just want a lesser index than this. So I just shift to the previous one and I have my pointer here. Similarly, I find the previous smallest element, and let's say it is here, maybe 2. Then I'm just going to take one more index than this. So I'll have the other pointer here. And all my area is like this. Bottleneck times the left minus the right minus left, right? So did you understand this complete solution? So this is for a particular bottleneck, and we will be assuming that at each iteration my current element is the bottleneck. So this guarantees a solution, and it's a complete solution. So you will always be able to find a solution, right? Okay, let's just look at the code. Like coding here is a bit easier than just visualizing it. So is the code. It's a very simple code. Like if you just look at the first portion, I have just figured out the next smallest element. So I just gave you a template for that monotonic stack, right? There I taught you about next greater element. Here I'm talking about next smaller element. So that was this case that I was talking about earlier. And you're going to maintain this data structure, right? So just black box this if you are a bit like struggling with the implementation, that you could look afterwards also. So in the first I have figured out uh, the right, I think the next smallest element, and in the below I have figured out the previous smallest element, and at the last I'm just doing this thing. So I figured out the right index, the left index. I'm subtracting L minus R, and obviously plus 1, and this should be multiplied with the bottleneck, which is the current element. And I am just maximizing my answer for each bottleneck. So I'll have the maximum area under my histogram, right? It's another standard problem. So nothing this problem has nothing to do, like just one simple observation was sufficient enough to solve this problem, right? So yeah. So let's look at this problem now. Okay, so let me just go back. If you have any doubts, like I'll redraw. I know that I'm not very good at drawing on board. So if you want me to redraw the diagram or explain that again, I'll do that. Obviously, I tried to have a Wacom setup, like I already have that, but there's due to congestion, I couldn't connect that. Okay. Let me give you a real example. Let me just simulate that. Let's just simulate that test case itself. 6 here. Now this is 6. Okay, now my algorithm says assume that current element is bottleneck. So I'm going to start with the first element, and I'm going to say, okay, my 6 is the bottleneck. So I need to find the next smallest element, right? The next smallest element and the right smallest element. Obviously, the right smallest element doesn't exist. Left smallest element doesn't exist. So for right, it is just the next element, which is 2. Right. So I'm just going to jump back. So I'm going to say this is the index where my next smallest element is present. I'm just going to jump back one index. So I'm again at here. And my like left should be 0 because it is assumed that this element would be there. Like it depends on your implementation, but this would again jump here. Like both the pointers would be here, and both the pointers would be at index 0, right? And what I'm doing in code is right minus left plus 1. So this is 0, so this is 1. So the area for this histogram, like including 6 as bottleneck, is just 6, right? So let's look at 2. So for 2, there is no, okay, so there is one right smallest element, right? Next smaller element is 1 here. So this is the next, so this is 5. For the previous one, it is like here, so it will jump here. That should be 0. So 5 minus 0 plus 1, it should be 6. It makes sense because you have 6 bars here. So it should be 6 into 2, which should be 12, right? So similarly, you could do this for 5. And if you go for 4, I'm just going to explain this test case. Next smaller is here. So it will jump to 5. You have at 5. So this is the right smaller. So they should jump here. So we have these 2 pointers here, and we'll just perform 4 times 4 minus 2, which is 2. Not 4 minus 2, I think. It is 4. Yeah, 4 minus 2 plus 1, which should be 12. Yeah. So there are 2 actually. So is it clear? I think it's 4 minus 0. It's 4 minus 0 plus 1. It's 5 into 2, which is 10. This was a mistake here. Yeah, you could just carry out the calculation. It was 10, not 12. So 12 is the maximum. So that is the case. I hope this is clear. So you just simulate this algorithm. And okay, why the time opacity is so often, you already know it is. I'm just finding the next. I could even generate the next greater element array, like two arrays for that. And I could just simply take right of that element minus left of that element plus 1 times that current element, right? Or you could use a single stack if you want to space optimize it. It depends on your implementation. Yeah, so is it clear? Okay, so let's look at the next problem. It's another interesting problem. I want you to understand this problem first. So I would like to like you guys to focus on the diagram. Essentially, what we are given is an array, and we need to find the maximum sliding window. Like if we consider a window size of 3, so we are given a number. So we are given an array, we are given a number, and that's essentially just the size of window you're considering. So let's say k is 3 and your array is 8 sized. So in the first iteration, you will be just looking at the first window, which is 1, 3 minus 1. You will be just outputting the maximum in that window, which is 3. So 1, 3 minus 1, maximum is 3. For the next thing, you just slide the window by one and you find the maximum for that. And similarly, for the further iterations, you could see -1, -3, 5. 5 is the maximum, so you just assign that, right? So you need to output this array. So, okay, so any approach, because in OA, if you think like if this type of question comes, then you need to score some points, right? So giving an approach is better than just not solving it. Okay, so I'm going to give you a situation. Suppose this is not typically an OA question. Actually, it is an interview question. So suppose an interview comes and the first question he'll ask is, why are you using a queue? So the numbers are changing. Then why can't I use a vector then, or array then? Uh, so, okay, so but I don't need a queue for that. I just need to move my pointers by one. If you want that, I can add two pointers, one at 0 and other at k, like something like I and I plus k kind of stuff. So I'll be just moving it. So I'll be considering that domain only, right? So yeah, so what you are trying to say, like I'm getting it, but give your complete solution. Guys, it's OA. Need to score some points. Yeah, yeah. K elements, we need to find the maximum, okay? Yeah, yeah. Hmm. Yeah. So your algorithm is, yeah, I got it. Your algorithm time complexity of k into n. So might be I'll again say 50%. K into n, because you will be iterating over that k sized loop for finding the maximum, and the other thing for just moving the pointer, like the initial pointer. So what you are essentially doing is I, j, and you're finding the maximum between these. But you have a special constraint here that j is I plus k, which reduces one loop. So that's why you are able to say it's O of k into n. Yeah. Okay, so you are using a single loop. So suppose, so first of all, you will be using this, right? I is less than n minus k kind of stuff, because you need to move your first pointer also, right? Your window moves by one at every point, and then you will be using a k loop, right? J equals to 0 to k. So it is k into n. Yeah. Like, okay, so what is the purpose then? Like, you are just iterating to reach that point only. Okay, so you are saying I'll find the maximum during that duration, right? Yeah, okay, so for the first time it will work, definitely. So 1 3 minus 1 minus 3. Okay, maybe I think, let me draw in 1 3 minus 1 minus 3 5 3 6 7. So you are saying I'll have two pointers here, and I'll move it till I reach the window size k. Is it that? You'll have two pointers I and j. and you will move on till you find this index, and you will keep track of the maximum. Okay, so I'm still not getting. If you want to find the maximum between two indices, are you calling this function? Yeah, custom is fine. That is fine. That functions is something that if you want modularization, you could use it. Exactly, because you are using a single variable to maintain the maximum, right? A single variable is not sufficient because it will store the current maximum only, right? It doesn't have memory to just think like, right? Just think about it and just clear everything.
Let's say at some point, let's say at some point you have these elements. Let's say 7, 3, 5, say 4. Okay. So let's say you want a window size of 3. So in this window size of 3, let's say you already have this window size. Now you need to include 4 into this window. So let's say you already have 7 as the maximum. So you won't consider this as the next maximum, but you also need to consider the 7 is going out in while you are changing this window to this window, and you now need to consider 5 as the next maximum. So like how would you be including 5 there?
In OA, you cannot do maybe, right? It is. It's not like he will give you maybe. I'll give you full marks, right? Yeah. Second maximum. Okay, so okay, so one thing, if you just try to calculate the second maximum, say there could be a situation like your first maximum is at here, like 9, and your second maximum is at here. So if you are planning like I'll just calculate both the maximums and I'll shift the window size, that's not true because this is the second maximum, this is the first one. Okay, in the first one you will say this is, but this would be completely removed when you perform the further iterations. Right? That is also true, right? Yeah. Based on index you will store. Yeah, that's the same thing, right? Whether you are considering this element or this index doesn't make any difference. Uh, First max, second max. So you will store the indices of the first max and second max, yeah. Okay. Time complexity would be k into n. You could check that out. Yeah. Okay. So all your approaches are fine. It is basically optimization problem. So all we have discussed are just optimization. Like it's not the real hard problems that you see that you have to develop an algorithm and you cannot think of any other approach other than exponential. So you are just reducing the time complexity from of k into n to some smaller value, right? So just think about what we are calculating extra. Okay, so one thing that, okay, let me just go to some observations and we'll have something. So yeah, I'll just directly jump to the approach behind this of an algorithm. And this viewpoint is from design perspective, so it might be a bit from the design, but I want you to focus on mainly the pattern here. So suppose that you are given that array, and let's say six, uh, let's say 3, 2, 1, 7, 4, and suppose 9 is there, and you are given some window size, right, which is very large, like this. And suppose you are standing here, then is there something that you could just avoid being like calculating the maximum? Could you avoid calculating the maximum for this whole subarray? Okay, so it is. So I'm just going to answer that then question. So yeah, next greater element. Okay, how is that going to help? Because my question is, I'm standing at 9, and let's say in some for loop in my original solution, that k into n solution, I was just jumping to 9, and I my next direction is going to be this to calculate the maximum, right? Then can I avoid these calculations? Okay, so I'm just going to answer the first one. So we could just ignore all these elements. Why should we proceed ahead? If we already know that 9 is the maximum till this array, till this subarray, 9 is maximum. So there is no point of just finding smaller elements than 9, right? It's again the same idea, like the idea behind the augmentation here. So you construct a data structure to maintain max element in a slot, and you need to fix all the violations and maintain the data structure. It's as simple as you could think of. So, and yeah, again, 2 and 3 guarantee a solution. I hope you are able to understand that. The same logic that I used earlier in this stack thing. Okay, so that's just the explanation behind my first point. And now that's the general strategy. So we need to build a data structure that allows us to remove all the smaller element than X in the current set in O of size. So this is my current set. Obviously, I can remove all of them, right? Using a single loop. So of size, that first thing is very simple. Second is max in the current set. How can we achieve that? Yeah, so again, that augmentation thing I just told. So a monotonic DQ solves this. So I'm just going to give you a brief idea of how what this is. Okay, suppose that I already have this current element as 9, right? The current element is 9. Then after altering my data structure, I'm guaranteed that my first element is going to be 9, right? If I find any larger element, say 10, then obviously all the elements are again going to be removed, right? Because I don't need to calculate for them. I have to remove all these elements and fix 10 at the front. So all the elements that could be inserted after 9 are the ones which are smaller than 9, which is 8, 9, or it might be, yeah. So once we have this data structure, we already have the maximum in the first position itself, right? Because if at any point we assume that, okay, my in this window my x was the maximum, then obviously it would have removed all the elements which were previously smaller than it. So x would already be at the front of my data structure. So that's how I achieve O of n maximum, right? And again, I'll leave it to you guys to understand why this is O of n. It's the same logic that we used earlier. It's weighted sum of size. because size of this data structure, like we are just removing, adding the elements and removing, but the only difference is that we are removing from the front and adding from the back, right? So you might have known about queues, which you insert like in this fashion, and whichever was first inserted, like this element was first inserted, then it should be removed, right? This is exactly what we want. We just want to remove all the elements from this side. But for queue, we cannot like add the elements, like remove the elements or add the elements at the front. So we need a doubly ended queue. Like it is, just consider that as a very flexible data structure that allows you to add the elements in the front and add or remove the elements at the back in constant time. So you do vector dot pushback. So there is also one function called push front, pop front. So Q has those operations. The DQ has those operations. That's the idea behind this data structure. And here's the like I didn't explain the whole design behind this problem, uh, like why exactly, like how exactly you implemented DQ and other stuff. That's carried out in this doc, which is not really required. I can say the purpose is not to just teach you design here, or like the idea is just to make everything clear at the front, but I want you guys to understand the idea behind it, so you would be able to recognize the pattern. So code will help you understand this better. So we have a DQ. So that's the syntax for DQ. And what exactly you are doing is, for the first key elements, so does anyone remember the templated code that I told earlier? The same template could be applied anywhere, these kind of problems. So you just use a for loop, you just iterate over all the elements, whatever range you want to consider. Then you just insert in my data structure. This is like inserting in my data structure. It could be monotonic stack, queue, anything you want, even set. Set will achieve this. The time complexity for that would be of log n log n. So depends on your ability, like which data structure you choose. Obviously, if you are not able to think about DQ, one thing that you could always think of is a set, because that's a flexible data structure. But there might be some problems with the implementation. That is one thing, because insertion and deletion at the beginning and end might be difficult. Like in general, you could use a set, but for some problems you cannot. So inserting my data, I just inserted at back. Obviously, I want to insert at the back. Then I'm just fixing the violation. What is the violation? I just want this kind of structure, so I can easily say this is my maximum, right? So what I'm doing is, all the elements which are smaller than this, just remove them, right? So if there were, suppose 5, 6, 7, it should be like something like 8, 7, 6, and 10 comes here. Obviously, all of them would be removed to get 10 at the first place, and this is to maintain the current maximum, right? So for the next thing, it's again the same thing. You'll notice two conditions are there, which are like perfectly fine. So one more condition is extra added, and that is for removing your. So your data structure might have something like this. So 10, it should be decreasing only. So 9, 8, 7, 6, it should be decreasing, because if it was increasing, then like some violation occurred here, then it would take over this and again adjust, right? So it might be possible that this is at index I, right? Maybe at 9, and this might be at 10, this might be at 16, 17, or something like that. And now you are considering case sized window. And it might be possible that this index is far more away from that window, the starting of that window. So we're just removing all the elements which are smaller than the starting point, right? Yeah, that's all about it. So very clean implementation. If you see, there's nothing doubtful about it. No corner cases at all, right? If you implement it cleverly, then you can even fix that one loop that I've written outside. That will save some lines of code. Right. So any doubts about this? It might be a bit new because, but these kind of questions, okay, are very standard. And by standard, I don't mean that they are easy or difficult or medium, but these are the questions that you should at least know. Because your OA would be set up like this. So all your questions would be based on this only. So you cannot say, I didn't know that question before, so this is hard. For other ITs, if you see, if they know, if they have practiced that problem and a similar problem comes, then they'll say it is easy because it is standard.
So from my experience, I would suggest this would be rather the first question that you can expect in a way. The first question being the easiest of all. So like to prepare such kind of question, basically it's a kind of a cakewalk or a basic question. So cakewalk or basic is the very first level that you kind of encounter while you solve a CP problem. So like these are the very basic cases. So like do have a practice over this.
Yeah, so I think I have taught the standard questions and now let's look at the actual problems. So yeah, let's solve something live. All right, so I've prepared some questions, and let's see. Like, I want you guys to solve this. Like, if you guys don't solve it, then let me just open this. So, are you guys able to see just a one-line statement? So, I can explain the question also. So, you are given an array and an integer k. All you need to do is find the length of the shortest non-empty subarray which has a sum of at least k. So you are given an array, maybe like A1, A2, A3, A4, A5, A6, and just take six-sided array. And suppose A2, the maximum here, like the shortest subarray of some at least k. Yeah. Let's suppose A2 and till A5 is greater than equal to take k. So A2 plus A3 plus A4 plus A5 is greater than equal to k. So that's a valid solution. I say that, yeah, this is one subarray which is greater than equal to k. I want to find the shortest amongst them. So it might be possible that A2 and A1 form uh, the sum which is greater than equal to k. So I want the smallest one to find this, or like smallest subarray which satisfies this property. So obviously this question could come in an way, but obviously it is on lead code, so you might not expect that. But if it was not on lead code, it might, because it's very similar to some standard problems. And just don't look at that lead code hard because it's not really that. In a way, you don't know. Yeah. So obviously, in a way, you need to give some solution rather than scoring zero. Then you could give some brute force approach at least. Okay, I think it might not be.
So before you start with the question, I'd just like to say a few words. So first thing, you should notice that the array also contains negative numbers. So just think like the approach would have been different if there were no negative numbers. But since here there are negative numbers, you need to think a different approach. So like keep your eyes open in these cases. Might be like you're considering a generic statement or a generic question in a way. And maybe it's possible that the question has such a strange constraint that kind of restricts the direction. So, like, keep your eyes open in such cases. Here you have an example test case where there is a negative number, so uh, do accordingly.
So okay, so I want at least some approach now. Okay, so one thing is that brute force should come to your mind instantly, because it might be possible that you are at the last minute. So like brute force is something that you should come up with instantly. So any brute force approach. Yeah. Yeah. So his approach is something like this: the brute force approach. You start at any index I, you have another pointer j, say like, yeah, and you just move on until you find the cumulative sum is greater than equal to k, and you just mark this as okay, this is one thing, and then you just increment your I ahead, and you perform the same, and you take the maximum, sorry, the minimum amongst the lengths. Yeah, so that's one thing. Sliding window. Okay. Okay, I think Soham clarified that point. Uh, okay, in sliding window also, if you were to choose a window of size k, like window of size L, then you just need to iterate over all window sizes, right? So k here is the sum that you want. It is the sum. And if you apply sliding window on that, you need to choose some window size for that. So you will be choosing, okay, this is I sized window or L sized window. Then you need to iterate for single sized window till n sized window. Remove the first element. We'll be removing the first element and then checking that. So at what point you will be removing that? So it might be possible that suppose you have an array, say 8, and you say that, okay, this doesn't matter to me, 7, 6, 5, and I'm very close to reaching my goal. Let's say, what is the sum here? 13 plus. So it's 22, I think. Not 22, 23, I think. So, uh, sorry, 21, yeah, sorry, 21. So if you think that I am very close to my goal, say 22, say 24 maybe, right? And I'm considering this, my total would be 23. I'm saying that I will be removing this element. It might be possible that the next element is -1, or the all elements are very large, negative. So removing this wasn't a good choice then, right? It might be possible that this is -1 and at the end you have 2. So if you were to remove this element, then your sum would still lag. Or like if it, yeah, 25 if it was, let's just say 24 only. Yeah. So this whole subarray will contribute to 24, and this would, this thing won't, this would be 23. Right? So these kind of cases are a result of over complication. So don't overcomplicate things, because we won't be able to fix every case here. Just think of something generic. Okay, so do you know what prefix sums, right? So obviously one thing that I notice here is sum. Maybe we can do something with the prefix sums. Okay, so now try to derive a formula for prefix sums. What is my modified conditions if I have my prefix sum array? Okay, so I'm just gonna write it. So all you want is prefix of j minus prefix of I should be greater than equal to k. Is it correct? So instead of just looping and finding, you just need some two indices and just say this is the case here. And now this should give you some intuition on how to solve. Just think of expanding, contracting the data structures, expanding, contracting, like we were doing before. We were expanding, we were just manipulating the data structure. It wasn't anything new. We were just removing, either removing from the front, removing from the back based on some condition, or maybe expanding on both sides. It might be possible. Just try to get something. Okay, now one question now. I think it's enough. 10 minutes should be enough to think about this. Okay. This whole problem actually. So prefix of j. Suppose I have prefix of j. I need to find what is the best possible prefix of I. Right. So suppose I find prefix of I. Let's say prefix of I, something I choose. I choose some prefix of I. It is something which is maximum amongst all the. Uh, let me draw in this side. All the other elements which are like prefix of I minus one kind of stuff. It is smaller than all these elements. It is smaller than all these elements which are on the left side. Then do I need to consider all these elements? Just ask. I don't need to, because this thing is minimum. If I choose anything left to it, it is going to increase my thing. So, and it is just increasing my length also, right? I minus one, so j minus I minus one would be 1 times plus 1, right? So which problem? Okay, so just tell me which pattern you notice from the three problems that we have discussed. We are trying to maintain something in the front, the smallest element in the front. Say it. Guys, at least say it. Which pattern? Guys, we discussed three problems. Okay, what was the first problem? Okay. How did we implement it? Okay, which data structure we used? Stack. Okay. So what was the second problem? Yeah. How did we implement it? Okay. Third problem. How did we implement it? Out of all these data structure, which is best suited for this? I want my smallest at the front. Yeah. Yeah. I just discussed the earlier thing where I was just having the maximum at the front. Now I'm just having the smallest at the front. So, so there are two kind of people. So if somebody says, I'll just remember and I'll just try out that question without understanding the concept behind it, then you would struggle with that, because this is not the maximum at different. It is smallest at different, right? So yeah, I think the implementation is very easy. Let's just see. I just calculated the prefix sum, and uh, I think you should be able to understand by this code itself, because it's very similar to the previous one. I'm doing is I'm just think about how you will implement this. So I have to use the loop, right? And just look at the last line, dq dot pushback I. I am definitely going to be pushing that in my data structure. That's one thing that I'm of course going to do. And above, both the loops are for just your violation, fixing the violations, right? So just the second last loop, the while loop, which is just above dq dot pushback I, what it is doing is it is just removing all the smaller elements, or all the bigger elements which were uh, above that, right? The same thing that we did, like all these things should be removed that we are doing. And in the above, we are just finding the answer. We are just removing. Okay, so that thing is something. So suppose you have this and you find, okay, I at I and j. This is already greater than equal to k, right? Then what if it is already greater than equal to k, I'm going to try for a shorter subarray, right? So I'm just gonna start popping here. I'm just gonna start popping until it becomes like either less than k, or the or the queue becomes empty. So this is the minimization step that I'm performing. That is the second last loop while loop. Yeah. Think calmly. This is like nothing special. It's like this exact same code that you see. And yeah, so the next problem is going to be taken by Swam.
So yeah, let's move to the next problem. It's called Frog Freddy. I honestly don't have much idea about this problem, so let's see. So we can go through the problem once. It says upper is relaxing beside a large pond where his pet frog Freddy is enjoying in the pond. The pond has n floating leaves, each defined by an x coordinate and a y coordinate as viewed from the sky. So just take 2 minutes to go through the question once, after which I can discuss. So let me just give you a gist of this whole question. It says there is a collection of leaves there. So it's basically denoted by an array of pairs. So let's say you have something like an array of pairs containing x1, y1, x2, y2, and this much. So like you consider this top element. There is a frog. You consider the top element, and like it jumps diagonally either towards the northeast or towards the northwest or towards the southeast or southwest by an element z. It's not given, I think. Yeah, it's not given. By an element z, and like you are given some directions mapping, like some of the alphabets mapping the direction. So like at the end, perhaps you'll be given a string of directions, and you need to find at which position it would finally rest on. Yeah. So this is the input format. So you'll be basically given a string and like a series of these points, and like this is your starting point. For this case, 5,6 would be the starting point, and according to this direction string that you have been given, you need to move along this path, and like you need to tell the final output, like the final position where it would be at the end. So here are some cases. Just note this thing. Like, yeah, there is a base case also. If there is no leaf in the direction, then Freddy doesn't move. So if it's like in that possible direction, there are no leaves present. So like you just need to stop there and wait for the next command. So any doubts here in the question? So if not, then could you guys just come up with a brute force idea of implementing the solution? Like a very brute force one. Like, okay, just see the limits ones. Here, n and k are in the range of 10,000. So, like one thing I'd just like to say, like normally for C++ implementation, in 1 second, you can perform 10 power 8 approx uh, calculations. So it's like, uh, I don't know, but n into k, like if your complexity is even n into k, then also it should pass, I think, all the cases in general, if you're not having any other like complicated calculation throughout your solution. So like you say me approach in this time, then we can maybe optimize it. You have a starting point, you'd be given a direction of, you're given a string of directions, and you need to move accordingly, and like you need to tell which is the final destination for this part. Any ideas? A very brute force one. Yeah, you need to go to the string, that's for sure. But like, how would we finding whether another point exists in that specific direction? Okay. Okay. So. Okay. So it's like the very brute force one is like you choose a point where you are in currently. Like you cannot even choose this point because of the like the motion that you'd be doing if you go as per this string, the string of directions. So at a particular point, you would just look in the whole of the string, or maybe you can look from some map that whether the next point exists, and not even the next point, you need to say the next point which is at the minimum distance from this point along the direction, right? Because say if you have points like this in this fashion, if you jump directly to this point, you could have chances of going in that direction, right? So you just need to choose this point because it's at the minimum distance to it and in the given direction as per the string. So like a very basic approach would be you are at this point, you traverse the whole array of this points, and like you find the one that's minimum to it, and you need to check this condition also that it hasn't been already taken. Most probably it wouldn't have been. No, there can be cases. Yeah, there can be cases. So you need to maintain another Boolean array maybe so as to ensure that this point hasn't been already taken. So like you can work accordingly. So there would be a condition like if this point hasn't been already taken, you consider finding the distance from that point, and among such points along the direction, you choose the one that has the minimum distance and that hasn't been already taken, right? Are you getting this point? Guys, any response, yes or no? Are you getting the point? If you have any doubt, please raise it. Uh, See here, Z, like you need to choose a Z. There is no particular Z that is given for a sentence. No, 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 no. It's up to you. Z value you need to choose, and it's better that if you choose the lowest one because you'd be getting more options to go along this direction, right? So, like, since you need to traverse the array every time, so for each point, say the string is of length k, or the string is of length s, perhaps. Let's see, n and m. I think they got some mistake here. So the string is of length k. So for each character in the string, you need to traverse the whole of this list of a pair of integers. So it's O of kn. So possibly, if the constraints are low enough and if they kind of satisfy this condition, it should have passed the 1 second time barrier. Although if it was a 0.2 second barrier, then you couldn't have passed it. We can't guess from here because maybe people could have done something else and we get a proper idea from here. So, so like this is a very brute force solution to it. I assume that this would not work in the 1 second time barrier. Given the solutions also that prove the same, maybe. So like I'd like you guys to come up with an optimized solution for this. Any ideas you have for optimizing the solution to maybe some login? Like do it in steps. Since you are now at O of n square kind of solution, so like rather than jumping to O of n, just jump to O of n log n and always try to look for an O of n log n solution. It's a very generic hint that like most of the constraints that you have will generally pass through this n log n time complexity, and that's kind of easier because it's just a matter of some sort or some binary search and you arrive at a solution, and it's pretty easy to think of. So maybe a kind of n log n approach. Guys, have anything on mind, like anything that you wish to share or like any doubts? If you have, it's okay. Any ideas? Like think for a minute. uh, let's see if you get any kind of ideas regarding this implementation. Our target is just an n log n. Somehow introduce the term log n here, removing one of this constant to power 1 factor. So this will do our job for sure. See, think in a kind of systematic manner. You shouldn't be just like searching for solution out of nowhere. Just think in a systematic manner. How can I reduce the problem space? See, for here, for a point, let's say you are at a point x comma y, you need to go, say, in this direction. Let's say it's just out of generality. You can choose any other direction. Let's say I choose this northeast direction. And like you kind of think, how can I reduce the problem space? So somehow you need to find out points that are along this line and away from this in this northeast direction. So like if you kind of reduce this thing to like to a particular line that moves along, maybe you can somehow reduce the problem space and maybe you can have better time complexities. So your first step would be to like to kind of sort out the points that are along the line along this direction. So like how can I do this? Remember, you're always taking a D step here, another D step here. So the slope is always going to be 1. So like to ensure the direction remains this, what do you guys actually need? Something like all points here on this line. You somehow needs to store this. Come on, guys. It's a very easy question. You somehow need a parameter through which you can store all these values that kind of lie on a line. What's that? Its slope is fixed. The slope is 45 degree, you know for sure, because d and d it's increasing this way. What else remains? Y is equals to mx plus c. What else remains? The constant, right? Let's see. So at x equals to 0, what remains is this constant. Hmm? Yeah. So it just remains y minus x, right? For this direction. For other directions, you can find accordingly. Like it's just a normal proof of work that you would just find this for other directions as well. So like once you have this point, like you can store it in a map. Let's say you store all the points of this in a map of vectors, right? So this is a map. You can keep a normal map or a kind of unordered map also. It's just up to you. And you store all the points along this direction. And what's the next step? You have an array, or maybe you maintain a set here. It's better if you maintain a set, or even an array would do the work because it's just a one-time thing. You just need to sort those elements according to their x components, maybe. Yeah, x components, you can sort them accordingly. So what's the next step? You're almost to the solution. You have just substantially reduced the solution space to y minus x, and it's the last step. You need to find the nearest element in this direction. You have a sorted array, binary search. So again, you have taken this component, and of course you have substantially reduced the whole problem space to a particular direction. So it would be kind of much more optimized than the basic n into key one. So this is how you arrive at a solution. Like you kind of think of how can you reduce the problem space, and this way things kind of like get easier for you. If you just search a solution out of nowhere that okay, I need to do something, I need to do something, and something else goes on your mind, you can't just like rely on that fact. You just like you need to streamline this whole process of thinking to a kind of optimal solution to this. So like I hope you can code this whole solution out. It's very trivial. You just need to maintain this map, and like you'd always be having this array, and it's better if you do it in a set because you need to remove the elements also. So it's better you use a set because st.erase, it's a direct function which removes a whole element out. And like all it remains is to just find the next element using a binary search technique, maybe lower bound or upper bound, probably lower bound in this case. So that's it for this question. I think the next question Harmit would take. So Harmit.
So guys, the next question is, we'll have two subparts and let's just look at it. Okay, I want your review on this. Just read out the question. Okay, so this is something that will scare you a lot. What do you think on the first go? If something like this appears on your OA, it actually is, it was asked in an OA. Just try to think, like the general format is going to be this only. The concept behind this is very, uh, like it's nothing, but they will just revolve, like they will just modify the question to look at scary. So, okay, so I want you guys to tell me what the question is. Okay, so, okay, before that, I think I should move to some easier version. Well, actually, this is hard, but the problem statement is easy. So you will find these kind of things out there. So you might look at a problem and say it is hard, and the other problem say it is easy, but it might be the other way around. So I'm just going to show you both the problem statement and let you decide which is easier. So yeah, just skip the first paragraph. Okay. One thing more, like in a way, you will get these kind of stories. So you won't have direct questions. It might be possible that they just plug in something like a story and just try to distract you from the actual problem statement. So yeah.
So here is another tip. Don't just go by the face of the problem. Problem with this seemingly hard mathematical question can be very easy if you cannot just transform this mathematical equation to simple English words. And a question like this in plain English words that are no mathematical terms can turn out to be a nightmare if you don't have an experience of solving such questions.
So yeah, like in lead code, you will have direct questions, but in way you will have these kind of questions. So here, like you need some experience with some like CP contests maybe.
See, for most of the OAs, the questions are kind of like they are kind of derived from the existing CP questions. It's just because they don't have that much of talent to start working new questions. So, like, if you have enough of practice, like you have solved the last couple of years' questions, all the questions that have been in all the contests happened over the last couple of years, from all say, I'm saying instead of very generic scenario, you have kind of the experience of solving all kinds of questions. So it's for sure that you can get the original question from this question we have been derived. So it's just like practicing more and more so that you can just figure out hold the question, actually ask how you.
So okay, so just explain the problem. Could you just figure out the actual question from this huge text? So like they will add some words like crush and other stuff to distract you, but that's basically their test. Yeah, we took all the subarrays of a given array. Yeah. Yeah. Yeah, correct, correct. So at least you figured out the question. And how does it seem easier than the previous? What's your opinion? Like, okay, let me just show the problem again. Does it seem easier than this? Yeah. Yeah, it's similar, but there is a bit difference. Here is maximum time something, right? Yeah. So the thing is that you have the exact same questions. Just the thing is that you will have some maximum out there, maximum of some subarray, and times like it would be a function, right? Function of this and min. Maybe you could say that, or something like that. So in this case, the function is like maximum times L minus R. Sorry, R minus L plus 1. Yeah. And in the previous one, it was the subtraction operation. Now, you might not notice, but in brute force, you will have some variety of cases there. So if a person tries to optimize this thing, so maximum minus minimum, then he can just directly do that. But in the other case, it might not be possible. Okay, like because it's a multiplication operation, it's not something that you could isolate. Okay, so which question you think we should solve first? Like only it's like one is dependent on other. If I solve one, the other is automatically solved. What you guys say? Or or should I? Okay, so given this problem, I have this function, right? And I know these are some operations like multiplication is there, or division is there. You know, this is not the challenge. Finding this is not the challenge, right? The main challenge is finding the maximum. So why don't I simply compute this thing? Like sum of maximum over all the subarrays. For this problem, it is like it has a very direct consequence because you need to find max minus minimum, maximum minus minimum. So if I just break the summation about this, then it would become something like this. I could solve them independently. And this is very standard. So this is very standard. So like you could find some GFG articles on this. And now, having taught you all of these, I think you should be able to answer what is the sum of maximum over all possible surveys. What do you guys say? Did you get any hints, or it's just a simple thing? It's just something that you need to pick.
One thing. See, one thing here is that like the brute force ones, you can just do this way. Like you take I and j, and you'll be finding the max or min element out of this. So people normally here get confused about that. They, they, they just don't get the fact that if you just want to pick the maximum or minimum from a subarray from I to j, like this would also result in extra O of n complexity because you'll be finding the minimum or maximum. You get it? So the overall complexity would be like O of n cube in this case. So like like it's too much. Even if it's O of n square, it was fine, but since you are taking a maximum or minimum out there, uh, the complexity would like rise up to O of n cube. Though like by using advanced methods you can just bring this down to O of n square log n. That's by using segment trees, or like these are kind of higher data structures. So like we don't, and we will be dealing with that. So we will be getting a very simple solutions out of here, and that's by utilizing a very peculiar fact about this question. Let's see how much you can like, get the fact.
Okay, here's a hint. Could you think backwards? You are thinking in the forward direction. I need this thing to be done. What if this thing, from where the source arrived, we are just looking at the destination, from where the, the thing arrived, could you look at that?
See, in the brute force solution, you'd always require an L and an R, or an I and an Z. So it's like you always require two independent variables while implementing a brute force solution, because you are kind of dealing with ranges here. So like since we need to bring the complexity down, so we just need to get out of this idea that I cannot have two independent variables. I just need to have one independent variable. So like you need to pick up something that's unique in this whole process. So what's that in this case? Something that's unique, just a single independent variable, and I can do the whole calculation on it. So this is how you'd be restricting this n power 1, and maybe there might be another log n term there, or it couldn't be also. But the fact is you cannot proceed in a normal brute force way. Just narrow it down to one element. So what is that one element? You guys can think of here one element among this whole range of L comma R. What's this one element? Come on, guys. One element out of this whole range of L comma R. That's what you are targeting, right? The mean or the max. That's the element you're targeting. So isn't it that this is a kind of a single unique variable which defines a whole space of L comma or multiple L comma R's? So like if you just pick this thing by its tail, by tail I mean by the element which is the max or mean in a range. So wouldn't it be that, like, I suppose every element in an array would contribute to some maximum or some minimum. So like I can get a count of how many maximum or minimums it is of, and like I can get a count of, like I can get a sum of the whole subarrays basically from that fact. So like you guys agree to this? Like we have brought this problem down from two independent variables to one independent variable. Any doubt? Okay, I think Herman can explain it better. So let's go with it.
Okay, so let's just look at the solution. So just take this case out there, right? Let me just say that. Okay, let me just clarify that the answer here is 5 only, right? So suppose you're considering some subarrays, right? Let me denote by this. Let's say 2, and let's say 3 is there. This is another subarray of size 1. There would be of size 2 also. So 2, 3 and 3, 1. And this should be 2, 3, 1. Right. So if you have like something like max here and min here, you can say it as 2 and 2 only. This is 3, 3 only, 1 and 1 only. And uh, this is 3 and 1. This is 3 and 1. So this is 0, 0. And yeah, okay, there are 2. So 3 3 1 is one thing, and 3 2 is one thing. I hope you are able to understand. uh, so this should, all three are 0. This should be 1, this should be 2, this should be 2. The answer is 5, right? Right. So in the earlier thing, I just divided that into a completely independent problem, right? Max minus min, summation of max over all subarrays. Let's just look at it. So I'm just gonna say, from where did this 2 come? Like, in how many subarrays is 2 the maximum element? Just think about it. So from here it is 1. From here, like, so maximum, so only one array is there in which 2 is maximum. Suppose I say, in how many arrays is 3 is maximum? So these are the arrays, right? There are 4 arrays. And suppose I know in how many arrays that element is maximum. So let's say ai is maximum in some k arrays. Then I just need to multiply with, like, I know the number of arrays, and I just multiply with ai. That should contribute to this sum, right? Max of L to R. So this is contribution of this element to this sum, where k is number of elements in which ai is maximum, right? Is it good? So suppose I find that out, then for the main I could simply do that. I need to find in how many arrays is this element the minimum, and I just calculate this and subtract ai times, let's call it k1 k2. So it should be ai times k1 minus k2. It's simple, right? And now the question is, our question is like now very simple. Question becomes how to find the number of subarrays in which a particular element is maximum. So it's again based on the patterns that I've told you in the first 3 problems. In how many arrays is ai the maximum? Okay, one thing, for to define an array, 2 indices are sufficient. That's one thing, and the current index is I. Correct. Uh, yeah, that's correct. Yeah, that's correct. So if we find the next greater element, say aj, then aj is going to be the maximum. Then this element wouldn't remain the maximum. Yeah, yeah. So that's on the right side. What if we do it on the left side? Right. And now, if I take any element from here to here, let's say a1, let's say this is b1. If I take any element from here to here, and then here to here, is going to contribute, right? So if I pick out any element, I will have these many options, right? So the number of subarrays would be, let's say, I minus k times L minus I plus 1, like L minus I, yeah, that, or R minus I. So that is J minus I, yeah. Is it good? So for an element, we find out the next largest element and the previous largest element, and all we need is this product times ai will give us the contribution to this sum, right? This solves this case. The maximum sum would be obtained, and the time complexity is not very, like, it is often only because you could pre-compute all the next greater, previous greater, anything, right? Next greater, you will have some loops, right? You could just use that pre-computed arrays to multiply them. So that's how you solve for this element contributing to the maximum. Similarly, if it is minimum, what can I say? It has to remain minimum in all these subarrays. So we need to find, yeah, that's correct. So we need to find the next minimum and the previous minimum, and the same contribution is there. Right? So if you just want to see the code, so like I don't really recommend you to go through the codes only if you are just really stuck, because this has some corner cases. This has some corner cases. So that's the the logic. So I have just, for readability, I have just used 4 loops. Like it's a bit lengthy, but you could have a single function to implement this. Like it depends on your implementation skills. So now, what about this problem? This was even easier because we didn't have to find the least and other stuff. Yeah, exactly. So once we figure out that maximum thing, we already know these elements, these endpoints. We already have them, so that's a constant. But this problem, there is some modular arithmetic, and maybe you need to learn some formulas for that because there's a modulo operation. And yeah, that's all about it. So you might this might seem scary, but the idea is nothing. Yeah, over to you, Son.
So before we could end up the session, I'd just like to say a few words about the implementation of such questions, wherein you need to look at both the sides from a particular index. Let's say you want the next Twitter elements from the left and from the right. So like this implementations can be shortened by kind of using a function. So let's have it in writing. So it's just a nice trick that you can apply uh, while you are running lesson time. So let's say you have some kind of array, and let's say you pick up this index, and you need to find the next better element from the right of it and from the left of it. So in this case, rather than using two while loops, just like do this way, like make a function. Let's say void ret maybe. I prefer writing a ret because that's a very generic name. You pass in this array, and you get an output array here. And inside this function, just considering the fact that it will only look towards the left or towards the right. Let's say I pick up towards the right, and it will pick up the next element towards its right, which is greater than this current element. And this would compute this for all elements in this array. This is the input array. So you just have one function wherein you can have an implementation of the same considering a fixed direction. For the other part, just reverse the array, the original array that you have been given. So the answer you'll be getting for the other part, let's see for the right one, it calculates the MAC to its right. For the left one, you just reverse this array, the original array you have, and pass it through this function. It would give you the array, considering the fact that it only checked to the left of it or to the right of the reversed array. So what you now need to do is just reverse the final returnable that this answer has written, and like this way, in a very short piece of code, you can implement both the things into one. You get it? It's a very nice trick. It's like reducing the amount of code that you need to write by half. So yeah, that's all for today. So if you guys have any kind of question or doubts, we are like up for it. Yeah. So another thing about the OAs. So in a typical OA, you can expect around about 3 to 4 questions, sometimes even 5. The first two questions, like this would be kind of cakewalk or easy. Like by cakewalk or easy, I mean the very first two questions or the very first 3 questions that we have done today. The next questions would be mostly from DP or graphs or the advanced concepts of DSA and CP. These days, the companies kind of focus more on CP, so the regular DSA stuff that you normally do on GFG or HackerRank, that doesn't apply. Like it's a trend, so there is nothing harm in it. So, like, this is how an OA would be. So, people would expect that you do at least 1 or 2 of the harder problems that you have. Let's see the last 3 of the 5 problem set that's given in an OA. So, like, do practice a lot. Like, given your situation, like, I saw a few of you struggle in the very first, the basics that we have discussed in the very first of the session. So, like, have a hold on it. People, especially the company guys, they would expect you to solve at least 1 or 2 harder problem. So your basics needs to be very like your basics needs to be perfect for solving those questions. Like upcoming the sessions would be mostly on DP or graphs, the advanced data structures and algorithms. So like be up for it, given that your intensives are like coming in 3 to 4 months, I guess. Like 2 months for the semester, another 2 months of summer break, and then you'll be having your interviews and your OAs for uh, your internships. So like do practice a lot if you wish to get placed or get an intern from a tech giant or the companies that like that visit our college. Yeah, that's it. Like you can expect the next session on maybe DP, maybe within a week or so. Let's see, we'll prompt you about this. The session is being recorded, and I hope we'll be sharing this recording on YouTube. Yeah, so that's it. If you have any doubt, we are up for it. Else, we're gonna close it.